So dear students, in the previous class we discussed about the conditions for a body to be in simple harmonic motion. So in today's class we will try to discuss about the projection of a circular motion executes simple harmonic motion on any diameter of a circle. So to understand the concept somewhat easily, we will have an animation here. So try to look at this animation so that it will be easy for you. So this is a circular motion. The particle is in the circular motion. So this is a particle. We are drawing one perpendicular here, and this is the foot of perpendicular. So how this foot of perpendicular is moving on this vertical diameter, you have to just analyze that. Observe that how it is moving, how the particle is moving. So when the particle is moving from this point to this point, the foot of perpendicular is moving from this point to this point. When it is moving from here to here, it is moving from here to again here. When it is moving up to here, it is completing one oscillation. And if you are plotting the movement of the foot of perpendicular on a graph paper, you will be getting a sinusoidal wave. So if you are taking on the vertical diameter, you will be getting the sine function, and if you are getting on the horizontal diameter, you will be getting the cos function. So in this way, you must be able to easily analyze how the foot of perpendicular is moving on the diameter. So observe this video. So in this, first the particle is starting from point y. The particle is starting from point y. So it is going from point y to x1. So foot of perpendicular, you can observe it is going from point O to x1. When it is going from x1 to y1, the foot of perpendicular is moving from x1 to O. When it is moving from y1 to x, the foot of perpendicular is moving from O to x. And when it is moving from x to y, particle is moving from x to y, the foot of perpendicular is moving from x to O. So by the time the particle is completing one circular motion or one rotation, the foot of perpendicular is completing one oscillation. So this is the animation you can observe here. Then coming to our actual explanation here. So in this is the actual diagram. So this is the foot of perpendicular. So when the particle is going from A to B, foot of perpendicular is going from O to B. When particle is going from B to C, foot of perpendicular is going from B to O. When particle is moving from C to D, foot of perpendicular is moving from O to D. When particle is moving from D to A, foot of perpendicular is moving from D to O. So by the time the particle is completing one rotation, the foot of perpendicular is making one oscillation. Now we have to obtain the equations for displacement, velocity and acceleration of this foot of perpendicular. This is nothing but projection which is executing simple harmonic motion. So first assume that the particle is at point P. Simply join the particle and the center of the circle. Assume that the radius of the circle is r. Simply drop a perpendicular from particle onto the vertical diameter. Wherever it is intersecting, this is the foot of perpendicular n. Okay, this is also called as projection. Now assume that the angular displacement of the particle is theta. It is nothing but equal to omega t, because angular displacement is equal to angular velocity into time. So if this is angle theta, this also will be equal to angle theta, because they are alternate angles. Now if you are observing this triangle OPN, this is nothing but a right angle triangle, and the distance from point O to point N, this is called as displacement. Remember, displacement is always measured from the center of circle. The center of circle is also called as mean position. So distance from O to N, that is called as displacement. Okay, now we have to obtain the equation for this displacement. So for that, from this triangle OPN, write for sin theta or sin omega t. So if you are writing for sin omega t here, you will be getting opposite side by hypotenuse, that is sin omega t equal to ON by OP. From that sin omega t equal to on is nothing but y and op is nothing but r. So taking this to left side, y is equal to r sin omega t. So this is the equation for displacement of a particle in simple harmonic motion. So in this also, if you are substituting two conditions, if omega t equal to 0 degrees, omega t equal to 0 degrees in the sense the particle will be at point A and the foot of perpendicular will be at point O. That is called mean position. Then if you are substituting that in this equation, sin 0 is 0, so you will be getting y is equal to 0. So displacement at the mean position becomes 0. Next, if you are substituting omega t equal to 90 degrees, that means the particle is at point B and foot of perpendicular is also at point B. Then if you are substituting 90 here, sin 90 is 1, so y is equal to r, that is nothing but the displacement is maximum. That point B and point D in the diagram, they are called as extreme points. Here point B and point D, these are called extreme points, and this is called mean position. So at the extreme points the displacement is maximum, at the mean point the displacement is minimum, that is equal to 0. Now coming to velocity. Velocity is simply nothing but displacement by time, that is nothing but we are adding a letter d, this is nothing but change in displacement by change in time, that is simply nothing but rate of change of displacement. So substitute the value of y in this equation. If you are substituting, you will be getting, that is d by dt of r sin omega t. In this, r is the radius of circle, or you can call it as amplitude. It is constant, so we are taking it outside the differentiation. So in the next step you will be getting v is equal to r into d by dt of sin omega t. So d by dt of sin function is nothing but cos function. So here we are writing it as v is equal to, that is cos r cos omega t, and this function again we have to differentiate d by dt of omega t. Next we know that v is equal to r cos omega t. Omega is a constant, so we are taking it outside, so d by dt of t, that is equal to 1. So v is equal to r cos omega t into omega into 1. So you can write it as v is equal to r omega cos omega t. This is the equation for velocity of a particle in simple harmonic motion. Now in this also we can have two conditions. If omega t equal to 0 degrees here, if you are substituting, you will be getting v equal to r omega into cos 0, that is nothing but 1. So you will be getting v is equal to r omega. In this also again, if you are substituting 90 degrees, cos 90 becomes 0, so velocity becomes 0. So this is pertaining to mean position. So at the mean position velocity is maximum, that is r omega. At extreme points the velocity is minimum, that is equal to 0. This is for velocity. Next coming to acceleration. General formula for acceleration is nothing but velocity divided by time. So change in velocity by change in time. So this is called rate of change of velocity, that is called acceleration. Substitute the velocity equation here. If you are substituting, you will be getting a is equal to d by dt of r omega cos omega t. This is the velocity equation. In this, r omega is constant, so taking it outside, you will be getting the equation a is equal to r omega into d by dt of cos omega t. So we have to differentiate the cos function first. So differentiation of cos function is nothing but minus sin omega t. So from this we will get r omega into minus sin omega t into again this omega t we have to differentiate. So d by dt of omega t. So in the next step you will be getting a is equal to minus, writing in the beginning, r omega into sin omega t into d by dt of omega t. So again omega is constant, so we are taking it outside here. So minus r omega sin omega t, omega is outside, so d by dt of t, again it becomes 1. So this becomes a equal to minus r omega square, because here omega into omega, into sin omega t into 1. So this is the equation for acceleration. A is equal to minus r omega square into sin omega t. In this also we can slightly modify the equation. So writing this minus omega square outside, so A equal to minus omega square, remaining terms we are writing in the brackets r sin omega t. But from the first equation we know that this r sin omega t is nothing but displacement. So that r sin omega t is the displacement, we are replacing it with y. So this equation can be written as this one. Now it can be written as A equal to minus omega square into y. This is also the equation for acceleration. So if you are comparing this equation with the general equation of simple harmonic motion, general equation for simple harmonic motion is A is equal to minus kx. Here also we are having A is equal to minus omega square y. That means acceleration is there, minus sign is there, x is the displacement and y is the displacement. So only omega square is treated as constant. So A equal to minus ky here. So this is representing the simple harmonic motion. So we can say that the foot of perpendicular is executing simple harmonic motion on the diameter of a circle. So that is nothing but the projection of circular motion is executing simple harmonic motion. In this also we can have two conditions. First condition is omega t equal to 0 degrees. If you are substituting this in this equation, you will be getting A is equal to minus omega square r into sine 0, that is 0. So A equal to 0, that is at the mean position. In the same way, if you are substituting omega t equal to 90 degrees here, then A is equal to minus omega square r from this equation here. Sine 90 becomes 1, so minus omega square r. So these are the values of acceleration at mean position here, and this is at extreme positions. So I must be able to remember the values. What are the values at the mean position and what are the values at the extreme points. So remember, at the mean position displacement becomes 0, and at the extreme points displacement becomes r. At the mean position velocity is r omega, and at the extreme points the velocity becomes 0. At the mean position the acceleration becomes 0, and at the extreme points the acceleration becomes minus omega square r. And these values, if you are plotting in the form of a graph, you will be getting the graph in this way. So this is the graph you are getting if you are plotting. So this first one, it is recording the displacement. This central line, this indicates the mean position, and this indicates the upper extreme point, and this indicates the lower extreme point, this dotted line, this one. So this is recording the displacement. So at the mean position displacement is 0, at the extreme points displacement is maximum. Here also at the extreme point displacement is maximum. This is mean position 0, this is also at 0. This is recording velocity graph. So at the mean position the velocity is maximum here, the graph is starting from here, okay, and at the extreme points, this is at the mean position velocity is maximum, okay. So here what happens here, the graph, if you are comparing these two things, wherever the displacement is 0 the velocity is maximum. Here also wherever the displacement is 0, here the velocity is maximum. Here the displacement is 0, here the velocity is maximum. So displacement is 0 at the mean position, but at the mean position the velocity is maximum. Same thing here, if you are observing, this is the mean position point. At this point the acceleration is becoming 0. So again this is the mean position point, the acceleration is becoming 0. Here also at the mean point the acceleration is 0. Okay, so at the extreme points if you are observing, this is corresponding to extreme point, this dotted line. So at the extreme point if you are observing, displacement is maximum, velocity is 0, but acceleration is maximum. So compare these two waveforms. Regarding displacement and acceleration, we have said that acceleration is always in opposite direction to displacement. Observe these two waves. If you are observing at this point, this is on the positive side, but this is on the negative side. This is on the negative side here, but this is on the positive side. So this waveform is exactly opposite to that of displacement. So we can say that acceleration is always in opposite direction to displacement. So this is about the projection of a circular motion on any diameter of the circle.